Welcome everybody. So this is the second, right, seminar in the analysis and math physics series, and we have the pleasure of having Alessio Figalli with us, who's of course spending the whole year, and he's going to talk about Serrin's overdetermined problem in rough domains.
Yeah.
Please, thank you.
So, first, it's a pleasure to be here. And when Camilo asked me to give a talk, I thought I shouldn't overlap with my Minerva lectures next week. So yeah, it's next door. So next week I will talk about obstacle problems, but this week I'm talking about something different, which is Serrin problem. And to introduce it, I would like first to probably remind you of a more classical result, which is, or let's say, a result that is more familiar to a broader audience, which is Alexandrov theorem. So Alexandrov in 1958 proved that by now classical results, which is the following. So you give me a domain E, so E in Rn, bounded and connected. And I'm going to assume the boundary of E to be smooth of class C2. And then Aristotle tells me that if the mean curvature of E is equal to a constant, then E should be equal to a ball. Okay. So it's a version of the supergeometric inequality, but for a critical point of the area. So you ask in curvature to be a constant, then the only thing can be a ball. It's important that you are connected, otherwise you will take union of balls. This is of course another example. And it's also important that you are bounded, otherwise you can start to be like cylinders or other objects. So how does the proof go? So I like to mention, because it's also the way Serrin proved this famous result about Serrin problem. So the kind of ideal proof goes through the moving plane. Moving planes method. So what is this? It's a very neat idea, very simple, but very neat. So let's say I have my domain. Let me draw a picture. And I will do it like very simple, flat in the plane. I'm going to take a plane, pi, let's say, and I'm going to start to move pi from outside E inside, so in this direction. So let me call, like I have a parameter lambda that represents, let's say, how much I moved. So for each lambda, this is lambda equals 0, let's say, and then I move the plane. So this is a different lambda, and this will be my pi lambda. And what happens is this. So you take the plane, you take your set on one side, and you reflect it on the other side. Okay, so from this part of the boundary, just flip it across this plane. And it will be a new surface that I'm going to call sigma lambda. And you see that at the very beginning, so for lambda, very small, at the beginning, sigma lambda will be contained inside my domain E. So this is my E. And then I keep doing this until something has to break. At some moment, I cannot do it anymore. What can happen? As I do this movement of sigma lambda, there are two things that can happen. So at some moment, first case, it could happen the following. So my domain, let me draw it in this way now for a moment. So this is my boundary of E.
Well, no longer remains C2, right? If you do this,
Sorry?
your domain will no longer remain C2.
No, but I'm just looking at this. This is a smooth C2 surface, and then I have another C2 surface.
Forget about what's outside.
Forget it, yes. And then, so what could happen at some moment is that, so I keep reflecting. So at the very beginning, you see it's nicely inside. But then at some moment, what could happen is that this is flat. And so as I reflect, I will reach a moment where the reflected surface here, sigma lambda, will be tangent here. So you will have that here you have boundary of E, and here you have sigma lambda, and here these two smooth surface arrive tangent. So at the very beginning, you see there is an angle just by continuity, but some of them could become tangent. And now what I observed, so I'm going to zoom in this picture. So I have here now my plane, and now I have my boundary of E. I have my other surface, and I just look what happens here nearby the tangent point. So I'm going to represent these as graphs. So I have U on the top, V on the bottom. So these two functions, U and V, satisfy a PDE because I can write the mean curvature condition in terms of these two functions. So the mean curvature of U, so the mean curvature of this boundary V, in terms of U, is divergence of grad U over square root of 1 plus grad U squared, and this is equal to constant. But now, what's the mean curvature of this surface? Well, this surface is just the reflection of this one. So the mean curvature is just the same. So the mean curvature here is this one here. But the mean curvature is constant everywhere. So this is also equal to the divergence of grad V over square root of 1 plus grad V squared. So both functions satisfy the same PD. And now if they're ordered by construction, use greater or equal than V. And now there is a PD theorem, which is called off maximum principle, that tells me that either U is identical to V, or the derivative, so the normal derivative here at the boundary, the slope there, so du over d nu at the boundary, so let's call this point x0, should be, in this case, this is the derivative strictly less than dv over d nu at the boundary. So either the two functions coincide or they have different normal derivatives. They cannot arrive tangent. So here I'm assuming that they're tangent. So this doesn't happen. So they have to be the same. So this means what? That in reality, this is not the picture. In reality, the picture is that my set E is this one, which means that E is symmetric with respect to this plane phi lambda bar. So lambda bar is the critical value where I have to stop. So when I stop, the only thing that can happen, if I stop because they're tangent, then they have to be the same. And so in fact, my set is symmetric. That's case one. So when they're tangent, there is another case. So it could be that my set is this now. And so this is E. I reflect. I reflect. And at this moment, what happens when I reflect is that this reflected here, it touches from this point. So the second thing that could happen as I move is either that they become tangent, or at some moment, this is boundary V, and here I have sigma lambda, and sigma lambda touches boundary V from the inside. In this case, what do? You take this picture, you move it here, you rotate, you have again this boundary V, and this is sigma lambda. And now you have again divergence of grad U over square root of 1 plus grad U squared equal to constant, equal to so now I'm representing this as graph of U, this is graph of V, divergence grad V over square root of 1 plus grad V squared. Here I have two functions which are ordered. Again, so in this case, I apply the strong maximum principle, which tells me that either, again, well, in this case, actually, they're ordered, they touch, there is no option. is equal to 1. So two functions solve the same PDE ordered at one point, they have to be the same. So again, what does it mean? That the picture is not this one. The picture is, if I touch, in reality, E was this set. So boundary of E and sigma lambda have to coincide. So again, also in this case, E is symmetric with respect to this plane. And now this argument, you can do it in every direction. I did it for this plane, I can do it for this plane, I can do for this plane, I can do it in every direction. So my set has to be symmetric with respect to every direction. The only option is above. So, E symmetric.
This was Alexandrov's argument.
This is Alexandrov, yeah. With respect to every plane. The only option is that E is above.
So good, you should stop there.
Yeah.
Such a great theorem, one doesn't want to change.
Yeah. But there is no T yet. So maybe I go stop here, but I won't. I'm sorry. So the question here that you can ask.
It would be nice if everything were that simple, right?
Yeah, it's a very beautiful argument. I love the Moore plane. You know, it has been generalized to many other settings. I will mention in a second once I reach Serrin how you do this for PDs. But before going that, just for completeness, so here you could ask, what if my set is non-smooth? Okay, here I use the smoothness. In particular, I assume that the boundary was smooth, C2, so that I could, you know, make this argument work. I need the smoothness. So, what if boundary is not C2? So the first thing you could do is, let's say, let's make it C1 or even a bit less. Let's think about the Lipschitz case. I mentioned Lipschitz just because that's the one that I will focus on later for Serrin. So you could ask boundary V just Lipschitz. You have to define the mean curvature. Okay, I will not enter into that. Let's think that you can define it in many ways. And mean curvature is constant.
How do you measure? No, I mean, what will happen?
Yeah, well, but then I assume that the distribution of mean curvature is a constant.
So it has a density, it's a constant density with respect to
the surface measures, and it's. But then, what can you do? Well, if it's Lipschitz, it means that locally my boundary. So this is my whatever my boundary doesn't matter. A priori could have corners. I mean, it's Lipschitz. But my boundary, I can still represent it locally as a graph. So I will have divergence of grad u over square root of 1 plus grad u square as a PDE locally, equal constant. And here we're in Princeton, you know, there is the famous De Giorgi-Nash theorem that actually tells me that if I have a solution to this PDE, then U is actually infinity. So in reality, there is nothing to do for Lipschitz. It's trivial, it's just PDE theory. I mean, there is a non-trivial theorem here. But once you have Lipschitz, solutions to this PDE are actually smooth. So in fact, there is nothing to be done. I mentioned this just because for Serrin will not be the case, or at least I don't know how to do it. Then you could say even more. So this is for Camille and Femini. Like, what about if boundary of E is? So what about if E is a set of finite perimeter? So this is just a GMT generalization of sets for which perimeter makes sense. You can define a mean curvature. There is a distribution of notional mean curvature. And the answer is that yes, E is a ball. And it is something that was done by Delgadino and Maggi in 2019. So this is true even in full generality, this theorem knowledge.
You need some assumption though. I mean, like touching balls. I mean, like, okay,
Yeah, you have to say again what is
connectedness.
connectedness. You have to talk about essential connectedness, but say if you connect that assumptions in this context, it works. And here, the key point here is that while here you can still run, so for Lipschitz, you just say I'm smooth, then I run moving plane method. Here you need a new proof. So the moving plane method for singular set is very delicate. And then they build up everything on a different argument due to Montiel and Ross. So there is an alternative proof of Alexandrov theorem based on some integral identities, and they work using that. And they build the proof based on that. Okay, why did I say that?
Mention somebody in Ross,
Montiel
Montiel.
and Ross.
and who's Ross?
Antonio Ross.
Antonio Ross is in Granada.
Granada, yeah.
So this is, they had a proof in 91, alternative proof of Alexandrov theorem. And starting from that proof, what we can imagine was to show that they could make this proof work in this constants of set of finite perimeter. They use the regularity of minimal surfaces, and blah blah blah. To
In dimension less than 8, if the problem for finite perimeter is classical, I mean, can you say already that the finite perimeter with constant mean curvature is regular, or I'm?
you don't have local. I'm not saying that you are local minimal surface.
Yeah, you're not saying.
I just say that the distribution of the derivative
sorry.
distribution of mean curvature is constant.
Okay.
I'm saying that you are local minimizing. If you have local minimality, then yes, you would have smoothness. But here is just this mean curvature constant.
Is it easy to say what the other proof is? It based on Bachner identities or something like this?
This other proof?
Yes.
No, they look like the distance function, and then essentially they take the set and they start to go inside with bolts. So they look at the set that you obtain by essentially going down with bolts of radius equal to the maximal curvature of the boundary. It's in, the proof of Montiel-Ross is in the smooth case. So in a sense, they write an area formula. So they start to go inside with the distance function with the normal, and they move. Essentially, if you're a ball and you move inside as much as the maximal curvature of 1 over the maximal curvature of the boundary, then you will reach the origin. So you will get just a point. And for a different set, you will get different geometry depending on the curvature. And then essentially what you do is that you write your set moving. I don't remember the details, but essentially you always move with the maximal ball that you can put inside. I don't know, maybe here, this is the maximal. At each point, you have a maximal ball that you can have from inside that touches. And you kind of reconstruct, you write a sort of area formula to reconstruct the volume of the set via this kind of race and integration. And then when you put everything together plus you apply some moment arithmetic geometric inequality to go from a volume term to a mean curvature term, and I use the mean curvature is constant and blah blah blah. Yeah. Also because the mean curvature.
You get a ball from an isoperimetric inequality or from a symmetry? I mean,
Where then? In the Montiel-Ross? No. You get essentially you get a bunch of inequality. At some moment you have an area formula, so something like 1 minus t curvature of the sets to the product of the I. But then you apply supermetric, the arithmetic geometric mean inequality. This is bounded by whatever sum. The product 1 over n is bounded by the sum, and then the mean curvature appears. So you apply 1. So this to the 1 over n, 1 minus th. H is a constant, and the constant is not any constant because you know the integral of the mean curvature times x to nu over a boundary of E is equal to n minus 1 the perimeter always. There is an integration by parts formula, and then if this is a constant, this should be the same as constant integral of the boundary of x to nu, and by Stokes' theorem, this is C n volume V.
Yeah, so then
So
you
you have
use
the-
isoperimetric. To get it a ball.
You get a what's called Heinzel-Kerkel inequality. So is an inverse isometric inequality, something like the volume is controlled by the integral over the boundary of one of the mean curvature controls something. So you have a Alexandrov type, like Alexandrov Fetcher type inequality with inverse mean curvature. So, I mean, I wasn't planning to speak on this, so I would have to reconstruct the proof, but I could do it, but maybe I don't want to spend now too much time. So what's Serrin now? Serrin is the PDE analog of this. So Serrin is the following. You give me a domain omega, and you define what's called its torsion function. So the torsion function is the function which satisfies the Laplacian of u equal -1 in omega, u equals 0 on the boundary of omega. So essentially your domain, and you have function u, which is kind of Laplacian -1, so it looks like sort of concave, and this vanishes on the boundary. So the name torsion comes from elasticity, and so this u exists and is unique. Let's say for nice domain, u is just the minimizer of the following energy, integral of grad v square over 2 minus V over omega. So you just minimize this energy, and the minimizer of this is this. So it's not so it exists, is unique, there is. And so it can this torsion function comes from elasticity, but there is also a fluid interpretation. And that's I think so I was reading the paper of Serrin the other day just to see how it motivates this problem. So the fluid interpretation is that you have an infinite pipe. Let's say you have a direction E, and the cross section of your pipe here, so it's a cylinder, and this cross section is your domain omega, so it's a 2D domain, and then you have the third direction, and then you have here inside this pipe a viscous incompressible fluids. That goes along the pipe. So the speed of the fluid, so U of x, so it's constant, the speed in the pipe, and U of x times E represents exactly the direction, the speed. So at each point x, the speed, so this is the speed of the fluid. So at the boundary U is 0, which means that so U on the boundary equals 0. This is what is called the Serrin's condition. So the fluid is doesn't move on the boundary.
Very viscous.
Very, very viscous on the boundary. It doesn't move. So viscous it doesn't move. And then you want to look at the stress generated on the pipe. So at each point you look at so you have your function U here, the speed, and du over d nu, the normal derivative of u at x on the boundary, is represented tangential stress on the pipe. Okay, so the fluid is putting some stress on the pipe, and now the question that was raised by Fosdick, who is a professor at the University of Minnesota, and Serrin was also there, was if the stress is constant, the stress is constant, so it's uniform, let's say, on the pipe, is the pipe circular?
So, but the flow is assumed to be, like the speed is assumed to depend only on the cross section.
Exactly. So
It's not depending on the third variable.
Yeah, that's why it's
So you are like in a steady
situation.
And then it's a solution of Navier-Stokes, actually, the one you're looking at. I think that's why you have Laplacian of u equal -1 or something.
Yeah, it should come from some steady solution of.
Yeah, I think it's actually.
And essentially, this is it doesn't depend on this variable. It's so steady. It's 0 on the boundary, and then you look at the stress, and the question is it true? Is it true that if the stress is uniform on the boundary, then the pipe has to be a round tube, or can I have a different geometry? So, so the theorem, Serrin.
What is the analog of mean curvature here?
So the mean curvature is this.
Okay.
So the theorem Serrin 1971, now I will write it. So omega is connected plus bounded. Boundary of omega is C1, is C2. So you take the solution of Laplacian u equal -1, u equals 0 on the boundary. So in omega on the boundary. And you assume that the stress, so du over d nu, is equal to constant on the boundary. Okay, so the function, this function u has the normal derivative constant on the boundary. Then omega is a ball. So this is the Serrin here. a bit of sport when you lift.
Yeah, yeah.
So just to mention, Serrin proof is based exactly on Alexandrov moving plane method. Just to explain how it works, the idea is that now, let's say this is my domain omega, and I have my function u here. I take some plane. Now the plane is in one variable more, pi, and I move it in this direction. So let's say now this is my plane that now it crosses. So this is like the graph of u on the plane by lambda. You have the graph of u here on this side. I will probably draw another picture in 2 dimensions. And then what you do is that you reflect it with respect to this plane. So you will have the graph of u in this direction. So maybe just a 1D picture. If this is my u, what you do, you start here, then somehow you start to reflect, and you look at the reflection, which is this. You take this part of the graph and you reflect it here. And you have now your u lambda, and then you start to keep moving, and then at some moment these two functions are ordered. You have u on top, u lambda on the bottom, and then as you move at some moment either they touch, or at some moment the graph becomes tangent, and you're going to apply again either strong maximum principle or not, or Hopf lemma to get that the function has to be symmetric. Same proof, the domain is a ball. So the function is radial and the domain is a ball. So this is the moving plane method to prove that solutions to PDE have to be radially symmetric. Okay. Now, what about if omega is not smooth? So this is here, this proof proves again smoothness. So let me maybe make just a remark here. So I have this condition u equals 0 on the boundary, and du over d nu equals c on the boundary. So I like to think c as a positive number. So to make it positive, I need to take nu to be the inner normal. So this is my omega, and u is the inner normal, and c is a positive number. Because my function is increasing. So my function is like this. U is like this, so if I want this number to be positive, I have to take nu in this direction. So the observation I want to make is that because u is 0 on the boundary, every tangential derivative of u will be 0. So saying that the normal derivative is a constant, this is equivalent to say that u is equal to 0 on the boundary, and the gradient of u is equal to a constant on the boundary. Because the normal derivative is the only component of the gradient. The gradient has no other components. It's only in the normal direction. Okay, so this is important because I will have to define at some moment what is a weak solution. What is a solution in a rough domain, and to do so I need to make this observation. So in 1992, Vogel considered the case where boundary of omega is C1, and then he considered again Laplacian u equal -1 in omega. U equals 0 on the boundary. And then you have to decide how you make sense of this condition. In which sense it satisfies this or this. You have to give me a definition. So in C1 domains, the solution to the PDE is not C1 up to the boundary. So this, you cannot interpret this in a pointwise sense. There's no gradient at the boundary. The domain is not regular enough. And so what he said is that he assumed that the gradient of u at x converges to C as x converges to the boundary of omega. So you put it as a limiting condition.
Sorry, Alessio, if it's C1 alpha, you can simply run the same argument, right?
Exactly. If it's C1 alpha, yes, because you have C1.
Because you have C1, so
Regularity, yes. So the only problem, I want C1 regularity even to run that. So
right.
C1 is the first non-trivial case.
Yeah, okay.
Because the gradient is not defined at the boundary.
You go to the boundary in any way, not, you could be coming tangentially.
Well, here C1 domain, so there is not many. Okay, you mean, yeah, this is really like uniform in the distance. So as the distance goes to 0, this one converges to C. And then, sorry. No, okay, sorry. I felt like someone was asking. And then what we proved is that in fact, in this case, you can apply Al-Caffarelli. This becomes a sort of free boundary problem. So they prove regularity for this, and they prove that in fact, if you are C1 and you have this, in fact, the boundary omega is C2. And then you are done. So it's a regularity, you have a regularity theory. Because you see, this is an overdetermined problem. You have both Dirichlet condition and Neumann condition. I mean, you have both Dirichlet and Neumann overdetermined. And this is a very classical free boundary type problem that has been studied a lot starting from the beginning of the 1980s by Alten and Caffarelli. And there is a lot of regularity theory for that. But it's the question which is subtle here is in which, so they have some note. So when you solve this problem in rough domain, you have to decide in which sense you solve the problem. And so it says that with this assumption is in the setting where you can apply the Al-Caffarelli theory. But there is somehow you have to check in which sense you solve the problem, and then maybe the two definitions don't match.
So in principle, if you take the definition, then you can always apply the regularity theory.
Right, but the regularity theory, exactly. So for C1 domains, it applies.
Yeah.
For Lipschitz domains, it applies. For less regular domain, it doesn't apply because you have singular sets. You get into like minimal surfaces. You may have a singular set in dimension, whatever. Well, up to now, we know that there are singular sets in dimension 7. Up to dimension 4, they don't exist, but a little bit of the parallel minimal surfaces. But you have to be in the setting where you can apply the theory. So he can apply it. Let me just mention that at some moment, Berestiki asked whether this theorem, the theorem of Serrin was true. For instance, if you just take a smooth C2 domain and you add a cusp, one cusp, can you still prove the theorem? This was solved in 98. But the question, if I ask you, boundary omega is Lipschitz. So I have to give you the definition. Let's say, what if it's Lipschitz? Unless you are in the Al-Caffarelli setting, which you can apply some regularity theory, this was open. So let me state let me explain for you what do I mean to be a solution of Serrin for Lipschitz domain. So you have to choose the definition. The definition that you need to apply free boundary theory, just for that makes it worse for the expert. Either you have to impose local minimality, which doesn't make sense because you're just looking at some PD, so there is no local minimality here. Or you should work in some sense of with viscosity solutions, which there is no reason here why you should. I mean, I don't see any viscosity in this formulation, right? So let's say I'm not in a situation where I can apply the theory. So what is the way to define it? So the way people have tend to define weak solution is the way we always do in PDE. Just you put all the derivatives on a test function. So let me give a definition of weak solution. So U is a weak solution of Serrin if, let's say, U is in W1 to 0 omega, so it's in a soluble space gradient inner 2, 0 on the boundary. So 0 on the boundary makes sense. W1 2 makes sense because just the minimal usually to define at least some weak derivative. And for every smooth function, integral over omega of grad U times grad phi. So let's look at this form. Let's integrate by parts. So this should be, if we do integration by parts, what you have? You have the integral over the boundary of omega. I put a minus because my derivative, my normal derivative is the inner, it's not the outer. So I have this. Then minus the integral of Laplacian U times phi. So this would be just the standard integration by parts form. Now, so this is the standard. Now let's assume that I solve Serrin. Serrin means this is equal to C, and this is equal to -1. So this should be equal to minus C integral over the boundary omega of phi plus integral omega of phi. For every phi, let's say C1 in other. So this is now my definition of weak solution. So U is a weak solution if this is equal to this.
It's not even clear that he can actually apply that criterion to this one, right? I mean, because you don't have enough regularity to say that you're converging in that strong sense.
Exactly. Yeah. So this that's very strong. In fact,
Yeah.
because we are asking the gradient to go uniformly to the constant as you apply, while this would be like the weak notion.
Right. So with this, even the state
Even C1 domains.
is not.
A priori. But let's say if I were C1, I would have a much simpler. But it's true. So that is not clear. And in fact, you wouldn't have that in general C1 domains. Okay, so this is my definition. Let me make it. Let's see if I want to say this extra thing or I want to. Yeah, maybe let me do, and we'll invert slightly the order to make it. Yeah. So theorem first. Yeah. So this is a joint work with Yi Zhang. Easier. Is that omega, let's say, connected, bounded, bounded omega Lipschitz. Then, with this definition, omega is a ball. So Serrin theorem works for Lipschitz domain. Okay. In reality, if you want, it's also true if omega set of finite perimeter such that you have an upper density. Bounded omega as an upper density. Let me not enter now. We can leave this density. We can leave these two questions.
You still assuming it's open or
No.
don't care?
No.
You just
No, I'm gonna prove that is an open set.
Okay.
So I need to give a definition, but it's just distribution. It makes sense for sets of finite perimeter. I have integration by parts formula, but you cannot assume W1 to 0, right? So you need just you just say that the function is 0 almost everywhere outside. It's W1 2 and almost everywhere outside, and then you have an integration by parts formula. So it makes sense. But let's focus on Lipschitz. I think that's already good enough to get the idea. The rest is technicality. So as I say, the difficulty here, so for Alexandrov theorem, there was the Georgi-Nash theorem that tells me if you're Lipschitz and you solve the problem, you're smooth, then you apply the smooth situation. Here, the hope could be, oh, if I'm Lipschitz, there is maybe Al Caffarelli who could tell me that in fact I'm smooth, and then I can apply Serrin again. But with this definition, I don't know how to apply the theory. We've been trying for quite some time. I don't see how to apply it, so we have to find a different proof. So, I mean, yeah. So let's try to play a bit with it. So there will be a couple of steps which are maybe a bit more technical, and I will leave them.
A different proof which proves Alexandrov directly, or a different proof which still proves regularity and then.
No, it will prove Alessandro directly. So it will be based on another paper that I will cite in a moment, due to Weinberger, which has an alternative proof for Serrin. So, so essentially there are few steps, and I think so. Some are kind of bit technical. So maybe I would just for the moment skip them and then we can discuss more later. So, proof. So the first thing I have to prove is an integral identity. So 1. I claim that if U is a solution of Serrin in that sense, then the integral omega of U is equal to C squared n over n plus 2 times the volume of omega. So it's an integral identity that gives me, so this is a bit the analog of what I was saying before. The constant is not a random constant, it's related to the data. And there is some identity connecting the constant C to the volume of the set and the integral of the function. So this identity, so there is a direct proof when if you assume that everything is smooth. So let me assume proof if all is nice. And this is what Weinberger did in 1971. So a few months after Serrin proved this theorem, Weinberger gave another proof of Serrin theorem. So they're actually published in the same volume of ARMA. First Serrin, and then a few pages later, this Weinberger proving, giving a new proof of Serrin. Okay, so how do you prove this integral identity if all is nice? So the way you prove it, I mean, you need to play a bit with the quantities. But the way you prove it is that so it's a classical fact that if U is let's say a function which has a nice Laplacian, harmonic or Laplacian constant, x dot grad U has also solves a nice PDE. So you look at the Laplacian of x dot grad U, the function x dot grad U, and you compute what this is. What is this? So the Laplacian has to go on the function. So you take, so Laplacian of a product is Laplacian on this plus, and this not differentiated, plus Laplacian on this and this not differentiated, plus twice, one gradient goes here and one gradient goes here. So you get Laplacian of x times grad U plus x dot grad Laplacian U plus twice gradient of x. Is this a matrix multiplied by the matrix gradient goes here, so echelon of U. Now, x, this is just a vector with components x1 to xn. You differentiate it twice, this is 0. Laplacian of x is 0. Gradient Laplacian of U is -1. So if you take the gradient of -1 is 0. And now gradient of x, this is the identity matrix. And if you multiply the identity matrix with the echelon, you contract, you get the Laplacian. So this is twice Laplacian. So these are always true when the Laplacian is a constant. And now Laplacian U is -1, so this is -2. So x dot grad U, the Laplacian of x dot grad U is -2. Okay. And now I'm going to do the following. I'm going to take my domain omega and integrate U against the Laplacian of x dot grad U minus x dot grad U against the Laplacian of U. So I put, you see, with a minus. And you see now in a second why, because now I'm going to do integration by parts. So I put, so this will be what? Minus the integral of U over the boundary times the normal derivative, the inner normal derivative of this. Now on the boundary I have also this, so x dot grad U times du over du when you do the normal derivative of this. So these are the boundary terms, and then minus, and then you integrate by parts, and you have gradient here, grad U times the gradient of this minus gradient of this times grad U. But you see, I have here a function f, function g, and here is gf with a minus. When I integrate, you see now I get grad U grad minus grad U grad. This is the same term. So these two terms just cancel together. So that's why I took the two functions, because now this is just the same expression. It's this function which is equal to this. And now here, I don't know what this is, but U on the boundary is 0. So this is also gone. And now I just have this term where this is a constant. And now what about here? I just computed the Laplacian of this is -2. So this is -2. And the Laplacian of this is -1. So you see that many things simplified. Well, let me keep the formula for the solution just for information. So let me copy this. I get -2 integral over omega of U. Minus maybe plus integral of x dot grad U over omega equal minus is plus, I think. I hope the signs are correct. I think, yeah. S dot grad U, sorry, on the boundary, and then times C. Okay, so like C on the boundary. Okay. Now, here I can integrate by parts again. When I integrate by parts, the gradient, there is no boundary term because u is 0 on the boundary. So this is minus integral over omega of divergence of x times u. And the divergence of x is n, right? Because it's just the sum over I from 1 to n of dxi of xi. I just differentiate the coordinate. So I just get n. What about here? So on the boundary, so this is boundary omega. Here I have the normal nu inside. So the gradient of u, I told you there is no, it has only one component, which is in the normal direction. So the gradient of u is equal to the modulus of the gradient times nu. So it's just a vector pointing in the direction of the inner normal. So this term is the same. So this is the same as constant integral of the boundary of modulus of grad u x dot nu. But on the boundary, I told you that the gradient is constant. So this is constant equals c. So I get c squared integral with the boundary omega of x dot nu. And now you apply the divergence theorem or Stokes, whatever. This is minus the integral. This is the inner normal, so I have a minus c squared volume of E. Again, so I'm just using that this is the same as minus the integral of the divergence. The flux of x is the integral of its divergence inside. The divergence of x is n. So you see, I have n c squared volume. Here I have 2 times the integral over omega of u, and here I have n times the integral over omega of u. So this term and this term equal to this term. And now when you just put everything together, you're back with that formula.
This thing is square. Oh, there is a square. It's not 2.
There's 2
There
n.
is a 2 plus n.
Oh, it says
Yeah.
c squared n. I thought it said c times 2n over n plus 2.
Ah, no. This is c squared.
He's talking about that.
Yeah, I'm there.
Oh, sorry.
Me also is like.
Oh, no. Sorry. Yeah, absolutely. C squared. Okay. So it's the square of. So I mean, the numbers have to be correct. Now, modulo signs, which I think are correct. So the key point is just take this identity, integrate by parts, and play with it. Now, of course, this is
So the role played by the vector field X is very big, and it has something eventually to do with sphere, I think. I mean, this vector field that he pulled out of his hat, yeah.
yeah, well, x dot grad u is a very common thing. It's using Pogosai's identity. I mean, it's something that with PD is not so surprising to use x dot grad as a vector field.
Well, maybe I'll wait for that.
Sure. Here, so for a long time, essentially, one main first difficulty for us was how do we reproduce this? So a lot of papers said, oh, Weinberger proof, for instance, one of the key things for Weinberger is to prove this identity. And you can prove it, of course, for domains which are weaker than C2, but you still have to make sense of all these integration by parts. You don't get to Lipschitz at all. So we managed, there is some preliminary work that I can mention more maybe later, but in a sense we managed because we found what is the right test function to put so to reproduce in them this identity. Okay, so we kind of put a test function there, phi, which is something like u1 plus epsilon x minus u1 minus epsilon x. So this mod over to epsilon. For epsilon small, this is like x dot grad u. Just make it a quotient, minus 2u of x. You take this test function, you plug it in that identity for epsilon, and then you have to show that things go as you want. It's not trivial. The difficulty here that there is some preliminary work is because you have to reconstruct this constant c and c squared. And this constant c is a bit hidden again in this integration by parts formula. So that's the part which, I mean, one c you have it, but you have to pull up a c squared. So there is another c that has to come up with this computation that you have to. So sometimes you have to find a way to incorporate the fact that this function has normal derivative equal to c. So there is some preliminary work and some estimates that we have to do before, but let's say then modulo technical estimates, this is the test function that in the smooth case will allow you to go from that identity to this identity. So you don't need to really do this. You can just plug it in and so actually plug in directly this and then work with that. Now, this is one step. So there is this sort of identity. The second thing you need is a maximum principle. So if you have an harmonic function in a domain, the maximum principle tells you that the function will attain its maximum on the boundary. So here, I want to apply this to the gradient. So, I want to prove that the gradient of u is less or equal than c inside omega. Okay, if I have a solution of Serrin. So in the smooth case, this is very easy. Let me show you how you do it with the maximum principle. So you know that the Laplacian of u is -1. So if you now you pick any direction E on the sphere and you differentiate, so you go to the Laplacian of dE u. So any partial derivative will be the same as the derivative of the Laplacian of u. So that's the derivative of -1, which is 0. So every partial derivative is harmonic. Okay. Now, what about the boundary? So this is the this is the omega. Now on the boundary, du is less or equal than the gradient of u, the full gradient. And in Serrin, the full gradient is a constant. So I have an harmonic function which is bounded by c on the boundary, so it's bounded by c everywhere by the weak maximum principle. So by maximum principle, I get dEu less or equal than c in omega. So this is true for every partial derivative. So I want to prove that the full gradient is the most of the gradient is bounded. So consider now. So consider. Consider x0 in omega closure. So I'm in the smooth case here, such that gradient of u at x0 is equal to the maximum over omega closure of the gradient of u. So you take a maximum point for the gradient, and now let E on the sphere be equal to the gradient of u at x0 over mod of grad u at x0. So you pick as direction the direction of the gradient at the maximum point. Then grad u at x0 is equal to d u at x0, and I proved that d was bounded by c. So I'm just proving that if every partial derivative is bounded by c, then the full modulus of the gradient is bounded by c. I mean, it's something extremely elementary. I could have proved also by proving that this is subharmonic, but I wanted to give this argument because that's the one that we can mimic. I wouldn't know how to prove directly that the full gradient. I don't know how to prove that with this definition the gradient is subharmonic in some sense, but I know how to prove the maximum principle for the partial derivative. So this will be in the smooth case, and we have been stuck for quite some time on how to do it with that definition. So just by knowing that, how do I prove that the gradient is bounded on C? So if I have a function u which satisfies this identity, I want to prove that the gradient is bounded by C everywhere inside. And here the trick, there is again a lot of preliminary estimate to prove that this makes sense, but you have to take, so you're gonna do the following. So, so in the general case, you fix, let's say, a point x0 in omega, and then you consider the green function centered at x0. So you consider the solution of Laplacian of the green function to be the delta at x0, and then gx0 equals 0 on the boundary. So we take the green function, and then I'm going to use here as test function phi the green function center at x0 translated. So by a direction minus the green function at x0 translated by the opposite direction. So minus over 2 epsilon. I'm going to take this is a sort of derivative of the green function. I plug it inside. I have to show that all the, I mean, the delicate terms come always when I work near the boundary. But then working with this test function and that PDE, we can prove that the derivative of in the direction E of U at x0 is bounded by 0.
You will regularize it first, though.
No. We first prove that the green function goes Lipschitz. So the first thing we have to prove is that in a domain solving this equation, and the green function is always Lipschitz up to the boundary. So we have to do some regularity estimates first on the green function.
Omega is not open at the moment, right?
No, we prove, for one of the first things we prove is that the omega is open.
Before this or after?
Yeah, before.
Okay. The green function is not,
Generally, the function is not Lipschitz up to the boundary.
I mean, it's always going to be similar in x0 though, right?
Oh,
Yeah, but this doesn't matter, right? Because near the boundary, what is near the boundary? You want it inside, no, but inside,
Yeah.
okay.
Okay, you will regularize it.
Yeah, but this is the inside is not a problem, right?
Okay.
I mean, there is no singularity. I mean, U is super smooth inside, right?
Yeah.
So-
No, I'm
sure.
just saying you will regularize it a little bit in inside and then you pass into the limit of the regularization to see that it's an admissible test for you.
Sure. I don't know. Okay, I thought yeah. Inside, of course, a priori is not C1, but
Yeah,
if you smooth
but
it out and you pass to the limit inside, there is no challenge. All the technicalities come how the green function behaves near the boundary.
Sure.
And since this is not a smooth domain, the green function is not regular in the boundary. And so you have to work. So it's a sense, just for the point is that we use the solution of Serrin as a barrier for the green function to the green function is Lipschitz up to the boundary.
Okay.
So
So
we have
you're
to-
not proving because it wouldn't be true on the Lipschitz domain.
No, the green function is not Lipschitz in a Lipschitz domain. But because there is
But because
because it's a
there-
domain that satisfies Serrin, that function controls this function. It uses works as a barrier for the green function. So there is some work to do. But let's say so. The funny thing here is that okay, this was for a long time when I thought this could have been the easy part, like maximum principle. Come on, it has to be true for Serrin, and it took us a lot of time. In fact, a lot of to prove it. And we had to pass through all this machinery. Just because my domain is not smooth. Okay, and now finally the final step is to consider the following function. P is gradient square plus 2 over nu. So this is Weinberger function. So this is how Weinberger concluded. You look at this function and you compute its Laplacian. It's a nice computation. Just write the formula for you directly. It's twice, if you develop everything, is dash of u plus 1 over n identity matrix squared. Which is a non-negative function. This is just an identity. You just compute, you have to use that the Laplacian of u is 1 inside, and you get this. So the function is subharmonic. So so I have my domain omega, right? Which apparently is not very regular. And u is 0 here. But if I look at u a slightly larger u, so I look at u greater than a constant theta positive, this will be a nicer domain inside, which will be super smooth, because u is super smooth inside. All the difficulty comes only near the boundary. Inside there is no regular problem. Laplacian u is -1. It's fantastic. So I look now this smaller domain and apply the maximum principle there. So I know that the maximum of P on the domain u greater or equal than eta is equal to the maximum of P over the boundary of u greater or equal than eta, so on u equal eta. And now on the boundary, well, grad u square, I prove that is bounded by c square, because I have 0.2, and it's bounded everywhere by c. And 2 over nu, this is bounded by 2 over n eta. So you let eta go to 0. So the maximum of P of omega, closure, let's say, well, the sup the support P over omega, as you let theta go to 0, is bounded by C squared. Just maximum principle by the domain, and then just let theta go to 0. Okay, so this is just maximum principle inside. And now let me use the last. I still have to use one, property one. Now property one comes in a second because this is the last part. So now I'm gonna.
This is not a problem for you because it's all inside.
Exactly. So this part
It's just literally the same.
This part is the same. But now it's all the same because I already, so most of the work for us has been to do this and that. Once I have these two, now you will see I conclude like in Van. So this part, it's okay. And now I just integrate P, so I know that C squared is greater than the integral. So C squared times the volume of omega is greater or equal than volume of omega times the supremum of P. This is greater or equal than the integral over omega of P. And now this is the integral over omega of gradu square plus 2 over n integral over omega of u. Okay. Now here I can integrate by parts. This is minus the integral over omega of u Laplacian u. There is no boundary term because u is 0 on the boundary. And Laplacian u is minus 1. So this is 1 plus 2 over n integral over omega of u. But the integral of u is that. So when you put this together, this is equal to C squared volume of omega.
So there's equality.
So there is equality everywhere. Every inequality must be an equality. In particular, this is an equality. So P has to be equal to its supremum. So P is constant. So this implies that P is constant, which implies that 0 is equal to the Laplacian of P. But the Laplacian of P is there. Is twice, let me remove this. Is twice the integral, sorry, is twice the echelon of u plus 1 over n and n. This implies echelon of u is equal to minus 1 over n identity, which implies that my function u of x is upper constant r squared minus minus x squared up to a constant translation, which means that omega is above the 0 level set. Omega is equal to PR. And that's that. Okay. So this is what Weinberger did. And here in the smooth case is just really these two identities. And in the singular case, the difficulty came because of the, well, essentially proving the maximum principle for the gradient and proving that identity. Just one last comment, I think. And now I have a weak chairman. Just one last comment is that this proof.
I don't think there's time for that.
Just this proof can be adapted to cover the case of slit domains. So I didn't find it on before, but like if I take a domain which is like instead of omega, so for instance, the domain omega is made of 2 half boats. Let's say even with a slit in between, doesn't matter. So you assume, think of this domain, you assume that at each point you have the normal derivative which is equal to C. So it means that here the function u makes a wedge. Yeah, so my function u will be like something like this. Here, like this. You can kind of repeat this argument. You have to properly define what is here the condition. I will not enter, but let's say our argument also covers the case of sets of finite perimeter with slits inside. So you can kind of make everything work, even if you have cuts inside the domain, which already for a disk with a cut, all the previous proof didn't work. Again, because they were all based on the regularity theory. But now with this method, you can cover that. So if you give me a domain like this with a cut, I assume that the normal derivative is constant everywhere. In fact, the cut doesn't exist. Again, you're a ball. And I think that's everything. So I stop here.
I have a question. Serrin problem is a linear problem. While the original one was in curvature was non-linear. This is completely irrelevant. In other words, this should be easy. In other words, I normally come to these and there's never anybody talking about linear PDE, so you made my day.
Well, it's linear.
Yeah, it's about the boundary, and of course but you're solving Laplacian u equals -1.
But the boundary,
Boundary
the
itself.
boundary enters in a non-linear way.
exactly.
I mean, curvature, yeah, so
Yeah, but it's not that Serrin would be easy. Also, Alexandrov would be easier if I mean the unicorn is like the only operator I could try to have. I mean, I could put other. Is the nicest, the more is the only geometric analog of Laplacian, right? But really, so you see the analogy very well in the moving plane, right? It's really
the moving plane argument.
You see, it's really the same problem. Now here, the main difficulty for us was really like, how do you deal with the weak definitions?
Yeah, right. Which you did.
And yeah, but I like a lot of Weinberger proof. It's nice.
That looks like the Montier and Ross. It's kind of the, you know, it's kind of the analog in some sense. Of course, whether you can make sense of a parallel between the computations is questionable, right? I mean,
yeah, but there are a lot of similarities in proofs between Alexandrov and Serrin. That's why I also wanted to make the parallel. But it was funny for me that I think
what's the analog of the Green's function in the nonlinear, in the mean curvature?
No, there I wouldn't know. I mean, here for me it's just a technical tool because I didn't know how to prove maximum principle for the gradient. So I had this very rough domain. I had a function which should be harmonic inside everywhere. But how do I make sense of the maximum principle? I didn't know. And then the only way I could do it was with the Green function. No, this is purely technical, right? I mean, how do you prove maximum principle?
I mean, if you want in principle, it's because you plug it into your identity and the Green's function, like that is kind of the derivative of the Green's function. So it's giving you the value of the function at that point.
Exactly. So that's how you define, in fact, yeah, this is how you can prove, with the derivative of the Green function, you give you the Poisson kernel or whatever, right? But in some sense, the difficulty is to give sense to that. Exactly. And so that's why we have these approximate derivatives.
Quick to explain how you prove that the Green function is Lipschitz using U as a barrier. So, I mean,
okay. The first thing you have to prove is that U is Lipschitz.
Okay, the U is okay.
Okay, so that's why I left some. So the fact that U is Lipschitz is not. So it's just the following. So you take a boundary point here. Okay, let's say the origin, and you look at how the function U grows on spheres. You do d over the R of the average over the BR of U. Right? And this is the integral over BR of the Laplacian of U divided by R to the n-1, and there is a constant Cn in front. This is like this is how you prove that for harmonic functions the mean value is constant. If you just do it as P, you get this. Now, what is the Laplacian of U? The Laplacian of U is -1 here inside, so it's negative. It goes in the right direction. But then there would be a distributional term here because my function does this. So it's 0 here and it's growing here. So there is a distributional term, and this distributional term, what is that? It's, if in the smooth case, would be C times the Hn-1 restricted to the boundary omega. So here I get Cn Hn-1 of the boundary omega intersection BR. So the area of the boundary BR over R to the n-1.
This is where the upper density.
Yeah, that's why you use the upper density.
Exactly. So if you are now, so if I set to finite perimeter, I'm going to assume that this is bounded.
And then
and then I get that this is bounded. And this implies exactly Lipschitz because now you integrate in R and you get that the average over BR of the is bounded by constant times R. And because of smooth inside, you prove that then implies that you use Lipschitz. And once you use Lipschitz, you see, so you use a function like this. So let me do it in 1D, the picture. Full day today.
Oh yeah, we have a talk in 5 minutes. Yes.
Oh, okay, then I stop. But you see, U is super harmonic, and the Green function is harmonic. One, I mean, a multiple of U will control the Green function. So the function cannot go, it has to go Lipschitz.
Yeah, so we have another talk.
Okay,
Thank
so-
you.
Yeah.